Hi, and welcome to this new tutorial about data structures. My name is Rosana Garcia, and today I am going to give you an introduction to what are the data structures, linked lists, queues, and trees. The agenda for this tutorial is the following. First, we are going to provide the theoretical instructions of what is a data structure and how linked list, queues, and tree works respectively. First, what is a data structure? First, we need to understand what is the meaning of the both parts of this term. What is data and what is a structure? A data is a value. As simple as it sounds, data is anything that represents something. However, data by itself have not really a meaning that can provide true important information to the users. Data, however, can be organized and ordered together, so they can be used to provide information about something or simulate behavior of the real world. That's where the part structure comes. A structure is an arrangement and organization of interrelated elements. Think of data structures like Lego blocks. When you see a Lego, you can identify that they have colors and they can be organized in different kinds, like the data types, integer, strings, doubles, and so on. However, they by themselves are limited if you don't organize them. If you provide them an organization of data such that they can represent something with that model, then you obtain what is a data structure. A model, an abstract model that represents something of the real life, just like the Lego can be used to represent cards, castles, and other things. First, we are going to start with the data structures called linked lists. What is a linked list? To understand this, we need first to understand what are pointers and nodes. A pointer is a variable that stores the memory address of another variable or value. You can see when you store data in the memory of the computer, you really don't know where it's located. However, for the computer to have access to these places, we use pointers. We don't know really how are the values of them at the moment. However, you know that they can provide the exact place where a data is stored in the memory, being it the hard drive or a USB. The nodes are also a data structure, a simple data structure that consists in a data, a value, and a pointer to another node. We use nodes and pointers to create what is called a linked list. A linked list is a linear data structure in which the elements are not stored continuously like arrays. When you use an array, usually you provide a size of how many elements can be stored on it, and it always going to come a point where that specific space is going to be reached, and you will not be able to store more data inside the array. Linked lists, however, can store as many elements as you want, since it's not limited to a specific space of memory. To be specific, the elements of the linked list are sparse through all the memory. And to keep track of where all of them are, we make use of pointers inside nodes. You can see an example. Here, the list is Juan, Jane, and Peter. That's not an array, that's a list. And we know that Juan is stored somewhere inside the memory, also Jane and also Peter. Then we create a node that stores the values. All those blocks represent nodes. The nodes contain the data that is the value, Juan, and pointers to the previous and the following value of the node. Juan is the first element, therefore there is no element before him, and then the node points to null. And we have a next element that is Jane. Then the pointer indicates where is located the node that contains the value j. As you can see, the values of the blocks are in blank because we don't know really what those values are. However, we know that they exist and they represent the direction in memory. When we have a node that only have one pointer to the following, however, doesn't have a second pointer to who was before, we have a simple linked list. If you have a node that contains a pointer to the following and to the previous node, then we have what is called a double linked list. Here is a representation of what I said before. We have a memory address, a block of memory, and it contains spaces or blocks that contains the data. And all of them have address. We are going to represent the address with integer values here, and they are from 1 to n numbers, as much as the memory can store. Next, we have the values Juan, Jane, and Peter. Even when you use index 1, 2, and 3 to access one, the reality is that you are accessing the position 34 in the memory address to access Juan, 246 to access Jane, and 231 to access Peter. As you can see, the order 1, 2, 3 of Juan, Jane, Peter is not the true order in the memory. However, the linked list allows you to have the illusion that they have an order, and that is the magic of this data structure. You can store as many as you want because it doesn't matter where they are located, you're always going to find them. The attributes for linked lists are the following. Each linked list consists of nodes, so they need to know what are the nodes attributes. The nodes attributes are the data that is going to be stored. It's an object, a simple type like integer, double, or more complex like classes. And we have then the attributes of the linked list that are the size, that is the number of elements inside the list, the head node, that is the first element, and the tail, that is the pointer to the last node. We have here an example of attributes for a double linked list. The functions for all of them are basically insert, remove, and save. Insert is to store a new element in the last position of the list, and remove is to take off that last element. Obviously, this requires an updating of the first and last elements. When you insert a new element, you need to update the tail, and when you remove it, you also need to update the tail. And the function size only returns what is the length of the linked list. Queues. A queue is a linear structure queue that follows a particular order operation. This order is called a FIFO, first in, first out. Unlike the linked list we told before, the first element in the add is the first element that have to take off when you take an element from the queue. Therefore, that's the big difference between a queue and a usual linked list. Actually, the linked list we described before can be used to represent a stack, another kind of data structure. We're not going to talk about this right now. We're going to focus in queues. The queues we have in this example have 5 elements. The colors represent the values of each one of the items, and the numbers above are the positions in the queue. We then have the functions in queue, that is the insert element, and the queue, that is to take off the first element. We can see the value green is stored in the last position. However, when we take one value from the queue, the first one in be taken off is the value in the position 1, and the index is updated. Queues have a different kind of behavior depending on how they are used. If we, for example, think in a bank queue, we can see that they may be ordered according to number or according to the time when they ingress in the queue. However, exists a different kind of behavior called the priority queues. A priority queues define that there are values that have priority over others. Therefore, they have to be the first in position so they can be attended first. In the example I am telling you about the bank queues, we have people of the third age and pregnant women. They need to be attended first because they are special cases. And therefore, if a pregnant woman appears, it doesn't matter if you have 1 hour of waiting, you need to give her the space so she can be attended first. This is a particular case of queue called the priority queue. However, even in priority queue, the first in, first out is kept. The priority have to keep the linear order of the first in, first out if they have the same priority. The queue attributes are similar to those of the list. They also have a length that represents the number of elements in the queue, and this is an integer value. And it also has 2 nodes, one that represents the first element and one that represents the last. Now we are going to talk about trees. A tree is a non-linear hierarchical data structure. What means non-linear in this case? A tree, different from queues and linked lists, doesn't have an order of how many nodes they are going to have. And the only order it can have is the fact that all of them start with one single node called the root. In the example we have in the right, we have a representation of what is called a binary tree. It has a starting node, the root, and the root is connected to 2 elements, 2 other nodes. And the nodes itself can be connected to 0, 1, or 2 nodes. And that is how the tree starts to grow. This is the basic representation of how a tree is. However, a tree in general is not limited to just 1 or 2 nodes. It can have 100 if required. And that's why this is a non-linear data structure, because you don't really have control of how many nodes are going to be linked to each other. And now we're going to have a little explanation of what is tree theory. Here you can review some of the terms we apply when talking about trees. You already know what a node is and what are roots. However, usually when you talk about trees, you're going to hear the term parent and child. A parent is a node that is connected to 1 or more nodes, and they are not directly connected to the root. To those child to reach the root, they have to go through you. If that's the case, then you are the parent of those nodes. And in this case, because you are the immediate ancestor, they become your child and you become their parent. The term leaf and branch is used to represent first and left the nodes that have no children. If you see in the example I told you before, you can see that the last 4 nodes have no connection with other besides the parent. Therefore, they are the left of the tree. And the branch are nodes that can be both child and parent. In this case, the only nodes that are both child and parent are the nodes in the middle, that have each one 2 nodes, child, and the parent node is the root. Here we have another set of tree theory terms, like sibling. Sibling node is the set of nodes that share the same parent. We have the term path. Path is a connection between nodes from the existing one to the root or to any other node of the tree. Something interesting of tree is that you can always reach a node from other because all of them have to pass at some point through the root. Therefore, there is always going to be a path that allows you to reach from one node to other. Here is an example of how trees can be applied to real life. And you have made at some moment of your life a family tree. A family tree consists in usually of your grandfather, your grandparents, your parents, and yourself with your siblings. It can start from many ancestors about your grandfather. However, the principle is the same. We have a starting node that is, in this case, let's say your grandfather, and your grandfather have two children in this case. And the two children at the same time have another children. We have the daughter. We see the daughter have two, and the father have three. And so the tree is going to start growing as long as there is descendants. And this is how family trees work. However, the trees can also be used to represent another type of relationship of real life. For example, Google Maps makes use of trees to know what are the paths that can be reached from a certain point. For example, if you're in your home, you want to know if there exists a path to one place to another, then Google Maps will find the path and all the points that represents the stop and other places that you need to reach before go to your goal is going to be the nodes of the tree. The point is that you can represent different kinds of real life events or elements through the use of trees. The example of family trees is just one of them. You can also represent a mathematical logic. And well, basically this is all we're going to talk in the tutorial. And this is only the theoretical part. And thank you for your time. And we have provided space in GitHub where you can find the code application in Python of all these data structures. There you can find more specifically the theory we are talking about, and you can read us step by step how the functions can be built and how all this data structure can be represented. There are many ways to represent in programming languages this data structure. However, we can provide you simple representation that can help you to understand how all this structure work, how they can be applied, and how they can be related one to another. Here is the link. You are welcome to join our tutorial anytime and have a great day. Goodbye.